Hello everyone and welcome to a new video. In this video we're going to ask ourselves the question, when does evidence become conclusive? In science this question comes up all the time, especially when results are questioned not because they are wrong but because they are uncomfortable or unexpected. We often hear things like maybe the setup matters, maybe a different variable is responsible, or maybe we just haven't tested enough yet. And those are reasonable questions at first. But science has a way of dealing with doubt. It doesn't ask whether a result can be questioned. It asks whether changing things actually changes the outcome. In this video, I want to show what good physical evidence looks like and how it becomes stronger, not weaker, when we deliberately change many variables. We'll start with a clear prediction, and then we'll try to break it by changing masses, energy input materials, and experimental conditions, and we'll see what survives. As usual, I'm going to do a kinetic energy experiment where I will be launching a pendulum, a little toy cart, and a wooden block with rubber bands and springs. Now, before doing any experiments, we need a clear theoretical prediction. In physics, the kinetic energy of an object depends on the square of its velocity. That means velocity does not increase linearly with energy. It increases with the square root of energy. So if I launch the same object with twice as much energy, for example, using two rubber bands instead of one, or two springs instead of one, the prediction is not that the velocity doubles. The prediction is that the velocity increases by a factor of square root of 2, which is about 1.4. And this prediction does not depend on the details of the launcher. It only depends on how much energy the object receives. And also, before we begin, here is a list with variables that will be changed during the experiments. We're talking about variables such as mass, energy input, launching mechanism, friction, and measurement methods. So here we can see the initial experimental setup. I have a pendulum with a mass attached on it. There is a stretched rubber band. There is a timing gate. I will pull back the pendulum to the clamp to make sure it will always be released from the same point. I'm pulling back the pendulum with my finger and I let it slide of my finger. On the left, you can see the time it took for the pendulum to go through the timing gate. As you can see, we mostly have a timing of 0.0064 seconds. All right, now I have added another rubber band. Let's see what happens. Okay, so the fastest timings were 0.0044 seconds. So the ratio becomes 64 over 44 equals 1.45. Hooray! This is very close to the predicted ratio of 1.4. So now I'm going to change the launching method. Instead of pulling it backwards, I'm going to push the pendulum and release it as quickly as possible. Let's see how much difference that makes. All right, so the timings on average were 68 and 52, which gives us a ratio of 1.3. This is a little bit below prediction, but not a dramatic difference. This time I will release it with a cable tie, letting the cable slowly slide of the pendulum. This is another variation of the release mechanism. Okay, the timings were on average 59 and 44, which is a ratio of 1.34. Again, just a little bit below prediction. Okay, now I have added extra masses, almost twice as much mass. The timings on average were 74 and 56, which is a ratio of 1.32. Next variable, instead of using rubber bands, I'm now using a spring. And now with two springs. Seems like we had average timings of 42 and 32, which gives a ratio of 1.31. Next variation, launching a toy cart instead of a pendulum. The average timings were 182 and 125, which gives us a ratio of 1.45. Next variation, counting frames instead of using the timing gate. Here is slow motion footage of the cart being released with one rubber band. Let's count how many frames it takes to travel from the 5 centimeters mark to the 2 centimeters mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here is the slow motion footage of the 2 rubber band launch. Let's count. 1, 2, 3, 4, 5, 6, 7, and with 8, it's already over the 2 centimeters mark. So we get 10 frames and around 7 frames, which gives us a ratio of 1.42. Last but not least, this time I'm going to release a wooden block using springs again as our energy input. Now we have 2 springs. It's a bit difficult to see because they are intertwined. The timings were 134 and 93, which gives us a ratio of 1.44. All right, let's now discuss the results. So I've changed quite a bunch of variables, such as the masses, the shapes of the masses. There was difference of friction, different velocities, different release methods, different energy inputs, etc. Here is an overview of the ratios. The average ratio of all the 8 experiments is 1.37, which is very close to the predicted value of 1.4. Now, what does this mean? The measurements vary, as real experiments always do, but they consistently cluster around the predicted value of square root of 2, and none support a linear relationship. The details of the setup do affect the measurements, distances change, forces change, and there is always some uncertainty. But what does not change is the relationship between them. When different masses, different energy inputs, different materials, and different measurement methods all lead to the same underlying pattern, that pattern is no longer tied to the experiment. It reflects something real about how the physical world behaves. This is how science builds confidence, not by relying on a single perfect experiment, but by observing relationships that remain consistent when the experiment is changed in every reasonable way. At that point, alternative explanations stop adding insight. They no longer predict new outcomes or explain the data better, and that is when evidence becomes conclusive. Not because doubt is impossible, but because the explanation keeps working when everything else is allowed to change. When multiple imperfect experiments all land near the same non-intuitive prediction, the agreement is not accidental, it's evidence. Thanks for watching.